Hello everyone, I am Chih-Shen. I'm a PhD student in Texas A&M University. My inventors are Dr. Arash Noshatrivan and Dr. Amir Bezidin. The presentation topic today is reliable post-disaster damage assessment using deep learning with uncertainty quantification. So let's start with the motivation. Recently, there are tons of machine learning and deep learning applications across various fields. Model reliability is always important, and for some applications can be very critical because error prediction may cause catastrophic or fatal outcomes. For example, the autonomous driving, medical diagnosis, and structural health monitoring (SHM) in civil engineering domain. And in the context of disaster management, damage assessment is key to successful post-disaster recovery because damage assessment is one of the key first steps in the process of seeking a federal major disaster declaration to assist the individual or the public entities recover. And artificial intelligence AI and deep learning division has been introduced this year to perform visual damage assessment. However, the high cost of the error decisions made upon this assessment result motivate a rigorous approach to propagate the uncertainty in the model predictions. And in the previous slide, we know that we can use AI for the visual damage assessment of buildings, like the figure below. This research aims to improve the AI-based post-disaster damage assessment using an uncertainty-aware convolutional neural network CNN model using the Bayesian inference. Moreover, we aim to develop a trustable neural network for the damage assessment. First of all, I will introduce the basic concept of the Bayesian deep learning because there are not any semantically rich dataset with annotations of disaster damage, and we need such dataset to train and test the deep learning models. So we create an in-house dataset based on the FEMA table. Next, I will present the model architecture, and finally, the presentation will be ended with the result and the contributions. Bayesian Framework or Bayesian inference provide a rigorous way to quantify the epistemic uncertainty of the prediction model. In Bayesian deep learning, we can think of the kernels or the weight in the neural networks are distributions, not deterministic numbers. So the output are also distributions. However, due to its intensive computational requirement, this model is intractable and hard to develop. Kendall and Gale in 2017 proposed to use dropout mechanism in the neural networks to approximate the Bayesian model inference, where the uncertainty and the output distribution can be estimated using Monte Carlo sampling. Here is a simple example of using dropout to capture the epistemic uncertainty. We create a simple network with only 2 layers to simulate a simple sine function. And the red points are the data point for the model training. And the black line is the model predictions. In the top figure, we can notice that the model do the extrapolation when x is larger than 6 and smaller than -6. You can see that in the orange sections. And if we use dropout for the training and testing, so the results are shown in the figure below. In addition to the model prediction, we can also have the confidence interval of the predictions. So as you can see, the uncertainty is larger in the regions of the red area because the model did not see the data points whose x is in these regions before. So in our research, we would like to build up an uncertainty-aware deep learning model for damage assessment. So the model input of is the building image, RGB image, and the output is the softmax distributions with confidence intervals. And this can help us to rigorously quantify the uncertainty of the model predictions. The in-house dataset was created using the web mining methodology from YouTube. And here is one of the videos that we have found and used. This UAV-based video captured the top view of the destructed residential areas in the Bahamas after Hurricane Dorian in 2019. We have collected 3 videos after Hurricane Dorian. So as shown in the figure, we use the label box to label the location of the buildings and their damage level in the selected frames. In total, we have created about 1,500 samples, which takes about 28 hours by one annotator. So the model is based on MobileNet, which has been pre-trained on ImageNet dataset. We use transfer learning to refine the model. And also, we added dropout to every layers, and these dropouts are active at both the training and testing phases. And here is the performance of the trained model. Overall, the model achieved 73% damage classification accuracy. At first glance, 73% seems not very promising. However, the human performance in similar scenario is around 70%, and the human judgment is also subjective, which would also yield the inconsistent results. So in addition to the accurate damage level prediction of our model, the model can output more information about the prediction uncertainty. And the figure illustrates an example of a building sample processed through our developed Bayesian deep learning architecture with dropout active at the inference time. The dropout of the model contains the mean value and their 90% confidence bound of the prediction. In this case, while the damage level 1, 2, and 3 exhibit the largest softmax means, which is around 28%, their confidence bound are relatively broader, which means that the uncertainty is higher. And additionally, the model has higher confidence because of a narrow bound, with the prediction that the building damage that does not belong to damage level 0, 4, and 5 because of the smaller softmax means. Overall, this probabilistic prediction can inform the final decision by saying that the damage level of this particular building is highly likely to be close to damage level 1, 2, or 3 due to their highest softmax means. At the same time, the model remains uncertain about the particular damage level within these 3 classes, either due to the insufficient information provided by the input image or because of the model has never seen this kind of image before during the training. So in this work, we train and validate an uncertainty-aware CNN model for visual damage assessment. Next, could quantify the model uncertainty. Unlike traditional dropout that is only active during the training, we utilize dropout mechanism both in the training and testing phases. Finally, the generated reliability information is critical to the post-disaster decision-making since it provides a more informative description of the building damage in support of further human assessment or distribution of the recovery resources. So I'm near to the end of the presentation, and I'll be very happy to answer any questions you may have. Thank you very much.